Hi, good evening.
Good evening, Dhananjay.
I have one question. Is it a good time?
Sure, is it? Yeah, you can ask.
Actually, already I have done the two assignment.
Mm-hmm.
The second assignment,
Okay.
question number 5.
Okay.
For a city of 9 lakh population, fire demand as per Kuchling formula is liter per minutes. They have given it. The
Okay.
Kuchling formula means equal to 3182 root of P.
Okay.
If I put this formula,
Mm-hmm.
I got the answer 3018710.
Okay.
I have selected the answer,
Okay.
but after the evaluation, the
Uh-huh.
answer is wrong.
Did
And
you put the population in thousands?
yes, 9 lakhs, root of 9 lakhs,
Okay. What is the answer that they're showing?
95460.
Okay. I'll look into it, Dhananjay, because I'm not discussing the assignment questions today. I'm just discussing some sample questions. So the Kuchling's formula and all will be shown. If
Okay,
your doubt is cleared that time, let me know. Otherwise, I will solve it and let you know what is the problem.
okay, fine, fine. Okay.
Dhananjay, are you there?
Yes, ma'am.
When I said you have to put the population in thousand, did you understand what I told? Because if you have a 9 lakh population, you have to convert it. You have to divide it by 1,000 and then use the value for P. Did you happen to do like that?
No, no. I have put it 3182 root
Okay.
of 9 lakhs continuously.
No. P should be represented in thousands. Like if it is 9 lakh, then it will be 9 lakh divided by 1,000. It's supposed to be 900,000. So you have to,
900, yes.
yeah. So you have to add 900 under root. Can you do the calculation and see when you put in 900, what is the answer?
8 minute, ma'am.
Sure.
Yeah, I got the answer 95460.
So that is the correct answer, right?
Yes, I understood.
Yeah. Okay.
Thank you, ma'am.
Okay, so hello everyone. Welcome to today's weekly session. This will be the second weekly session, and we will be discussing about we'll be discussing some sample problems that will help you in solving the assignment questions. So this week I was considering solving the third week's question, and after that the second week, because you're supposed to be submitting the second week's assignment. The third week's assignment by 15th February. So I'll discuss the week three's sample questions, and after that we'll go back to week two's sample questions, which is on water demand and population and all. And before that, I think I'm not sure if it was Kiran Behra. Last time, was it you who asked what was the pattern, what the pattern for exam will be for?
Yes, ma'am. Good evening, ma'am. I only asked it. Yes.
Okay. Actually, the exam is going to be an MCQ exam. It won't be descriptive in nature. Certain questions would be there where you'll need to fill in the blanks. Other than that, it will be multiple choice questions.
Okay, ma'am. Thank you, ma'am.
Okay. So we'll start with our today's session. So before we go on to the questions, okay, so before we go on to the questions, these were the lectures that were covered in the second week and the third week. I'm audible, right? Could someone show a thumbs up or unmute your mic and say, I hope I'm clear to all of you.
Yes, you are audible.
Thank you, Sangamita. Okay, so second week and third week, these were the lectures that were taken: concept of water demand, components of water demand, fluctuations in water demand, population forecasting, demand forecasting, and design capacities. And in the third week, it's about water sources and intake structures. And these are the topics that have been covered in all these lectures. Lecture 6 and 7, these are the topics about basics of what is water demand in the lecture 6. In the lecture 7, they're discussing about different types of water demands: firefighting demand, industrial demand, per capita demand, commercial and institutional water demand, and what are the standard norms for various water demands. In lecture 8 and 9, again, what they're discussing further topics about water demand, about the factors, the fluctuations, what are the kinds of variations. And moving on to 9, we enter into the population forecasting, the necessary different techniques of population forecasting. In the 10th lecture, which ends the week 2 lecture, there's future demand estimation, estimation of demand-based design capacities, and few worked out examples. In lecture 11, we are moving on to, that is the starting of the week 3. We have moved on to water sources and what are the different types of sources of water. Then water intake structures, different types of intake structures, and a little bit of details into that. Then we are entering more into the groundwater system, the aquifer systems, and related terms and theory behind it. Lecture 14 and 15 covers that. Lecture 16 is based on certain conveyance of water system, how water is conveyed from the intake to the point of supply, and about pumps and examples relating to aquifers and pumping tests, etc. Now, like I said, we'll move on to the third week's questions, some certain sample questions. So like last time, I'll give you some time to go through the question, and you can drop in your answers in the chat box, and then I'll give you an explanation to the answer for the question. So the first question is this one: what is the criteria for selecting water sources? Is it long-term availability of good quality of water, distance of the source, and or cost of water expansion? So there are 7 of you. It would be nice if you could answer the question simultaneously and go. So the session would be a little more interactive, and it will also be helpful for you to study now and go on. So Dhananjayan has solely replied and he says it's D, which is correct. So these are the criteria for water selection, water source selection. Majorly, there are 4 criteria based on which we need to. Yeah, Kiran, your answer is also right. 4 criteria are there. Characteristics of the source of water. That includes if the availability of water in the water source is sufficient, whether it is only available for a particular amount of time, or whether it is available for a long period of time. Like there are certain rivers or lakes that gets dry during summer. So is it okay if we can use that as a source of water? Then again, the water quality is a important criteria. Moving on, excuse me. Moving on, what uh, if the water source is susceptible to pollution, and also the accessibility to the source is also one important criteria for water source. Now moving on to the geographical properties, whether what is the distance between the point of water consumption and from the source, whether there are enough infrastructures that we can install to construct an intake structure or a storage structure to make use of that water. What is the soil type there, whether we can, is it suitable for installing a water conveyance system, or is there an elevated terrain near to the source, so that in case of making a water storage structure, we'll get good height over there, pressure head over there. Also, the economics and cost is a very important factor, and also there has to be a system near to the source, that or a system where the source exists, where stage wise development and planning and all is possible. So the answer is all of the above. All these options are important criteria for selecting a water source. Moving on to the second question. For surface water intake, the common type of shape provided for water entry through the inlet pipe of raw water from the collection unit is it a concave type entry, a bell mouth type entry, flat type entry, or none of the above? Okay. P. Sangamitra. Sangamitra, is your name Sangamitra, or I can call you Sangamitra, right?
Yes, yes. My name is
Okay.
Sangamitra.
Okay, okay. So because there's an initial, I don't know if it is, if that is your first name.
No, that is my certificate name, P. Sangamitra.
Okay,
So title is not written.
Okay, okay, okay. So Sangamitra, Mekandatevan, Bhavya all have replied B, which is the correct answer. So Bellmouth entry is the most common type of entry that is provided for an intake structure. If you see here, this is a river intake, and you can see. Okay, so you can see this point over here. Okay, my laser point is not working, so I don't think it's a good idea. I'll switch it off. Okay, this over here near the intake structure is what you see, mushroom shaped thing. That is the bell mouth entry. I'll show you another figure. The bell mouth entry means it's in this form. It's like a conical funnel-like structure that will be kept over there, and water will enter through that. So this is the most common type of entry that you see in intake structures. Moving on to the third question. You are given certain options of sources, and what are the sources? You just need to match with those appropriate sources. Yes. Kiran has said D, Sangamitra D, Mekanta Devan has said D, and all of you are very well informed, and yes, the answer is also D. So here are some examples of surface water sources: springs, lakes, ponds, rivers, reservoirs. All these are examples of surface water sources. If we go to groundwater sources, again, aquifers are groundwater sources, artificially recharged groundwater. All these are groundwater sources, as the name suggests. Atmospheric water sources, rain and storm water. Recycled wastewater is also a source of water, but again, it's a very unconventional source of water. Brackish or saline water, that also is not a very common source, but again, it can be used after desalining ethanol, which is not very common. So here they have asked what is a groundwater source? It's aquifer. Number 2, atmospheric sources, rainwater. Unconventional sources, recycled wastewater. Surface water sources, lake. So it's option D. Okay, so the fourth question: river intakes, if situated in a navigation channel, have a method of protection. What kind of method is that in the as mentioned in the following options? Is it by providing a wire mesh on the intake inlets, or is it by constructing a deep intake foundation, or constructing a cluster of piles around the intake, or is it all the three options? Okay, so few of you have given D as the option, and I'll move on to the answer. The answer is C actually. So here, if you see in this point, generally an intake should not be constructed in a navigation channel. Now, suppose if it is constructed, then we have to provide a cluster of piles around this intake structure, so that when boats or ships are moving across it, the force of the water is not affecting the intake structure. So the option is C. Constructing a cluster of piles all around the intake is what is the necessary measure that has to be taken in a river intake if it is being constructed in a navigation channel. Generally, it is not constructed, but again, if it is to be constructed, a pile structure should be provided around the intake. If you refer to slide number 14, the details are there. This slide has the details of design considerations for an intake structure. Question number 5, for a pumping well with discharge of Q, the drawdown is given by BQ plus CQ square. What is B and C in this equation? I don't see any answer coming. I think everyone is yet to go through the week 3 lectures, I believe, but nonetheless, this is a very it's a very probable question that can come. Even if you don't go through the lectures, this is something very superficial in the topics in aquifers. So this would be good information to you before you go and see the lectures. So I believe there aren't many who are well informed about that part of the lectures. So okay. So if you see here, if you go deeper into the aquifers, there is a portion for considering the well losses in well hydraulics. So in that, there is a term called drawdown. A drawdown is when you pump out water from a well, the water goes down by some height. So that height is called the drawdown. This is the original surface of the wall. If this was how where the water level was in the beginning, when you pump it out of this well, the water level will go down this much. This distance is called the drawdown. And when water is pumped out of here, the water profile of the aquifer is going to look like this. This will be the drawdown curve, and this cone is called the cone of depression. So in this drawdown is equal to BQ plus CQ to the power n, and B here indicates the losses due to aquifer, and C here indicates the losses due to well loss. So this is the formula for drawdown, BQ plus CQ square. B indicates well losses, sorry, aquifer losses, and C indicates well losses. And generally, there are two formulas, Jacob and Cooper and Thies formula. According to Jacob and Cooper, they generally provide n is equal to 2 value. Again, if you go through the slides in detail, you can read about it. So for this question, the answer is option A, aquifer loss coefficient, and C is well loss coefficient. Moving on to the sixth question. For a pumping well located 100 meter away, left to a river. So a well is there, it is located, there is a river, there's a pumping well located 100 meters left to the river. What is the net drawdown estimated by superimposing drawdown due to discharge well with drawdown due to an image well that is having a same pumping rate? Okay, so I don't see much answers here for this question also. So I'll move to the explanation. So in here, what you see is, again, we are talking about the pumping of water from a well, discharge well. So when you pump out water, like I mentioned earlier, water will be pumped out, this cone of depression will be formed. But when there's a river or something which is close by to this discharge well, what happens is the cone of depression, if you see here, I think I'll have to put the laser on. If you see here, the cone of depression is given. Yeah, this is the cone of depression. Actually, the cone of depression has to follow this profile. But since there's a recharge constant head boundary condition over here, the water level is going to meet with the head of the river, which is actually not, which is actually making it difficult to compute what is the drawdown, what will be the actual drawdown of this well. So in order to compute the drawdown of the well, what we do is exactly at the distance of this well from this boundary, we will consider, assume one imaginary well, opposite type. It will be a pumping well, but it will be putting in water. Here, this is discharging water, but this well we'll assume it as a water that is recharging, and we'll find out the drawdown for the cone of impression. So this, since there's no boundary condition, will give a drawdown height that is equivalent to the drawdown depth of this well if there was no recharge well. So in this case, what is being followed is the principle of superposition. Again, it is there in the lecture notes, and you will understand once you go through the lecture notes. So what is happening here is, we are going to imagine or assume an imaginary recharge well. That is, since here it is a discharge well, here we'll assume a recharge well that is at the same distance of as the well from this boundary with the same pumping rate. So if it is being discharged at a rate of Q, here water will be recharged with a rate of Q. So the answer is an image recharge well located 100 meter away on the right side to the river. And also it will be on the opposite side of the river from where the actual well is located. So for an aquifer bounded with a recharge condition, imaginary recharging well with the same pumping rate and distance on the opposite side of the boundary from the real well is used for estimating drawdown. Now moving to the next question. Identify the correct statements regarding the appropriate location of an intake for water supply. The intake should be located at the downstream of a disposal point, or the intake should enable water withdrawal during floods as well as dry periods. The intake should be at a considerable distance from the treatment plant to protect water quality. Even if you have not gone through the lectures, maybe you can take a guess, because this is, you can just think about if there's an intake structure that is being constructed, what should be the conditions. Yes, Kiran, Dhananjay, Bhavya, Kandatevan, Sangamitra all have answered. You've answered one of you have answered it as D, I believe. The other says C. Correct answer is C. So these are the necessities of necessities or the criteria to be taken care of when we talk about the location of an intake structure. So it should be near to the treatment plant. Moreover, it should not be located at the downstream of disposal, because we know why. If it is located at 1 second. Yeah, if it is located at the downstream of wastewater, then we know that it is going to be polluted. Then it should also meet the water demand during flood periods as well as during dry spells or during drought conditions. And also it has to be accessible at both conditions. Even during floods, it should be located in such a place where we can access it for whatever necessary work. And also it should not interfere with river traffic. Again, that is why we don't prefer setting up a intake structure and navigation channels. So these are the conditions to be taken care of when in terms of the location of an intake. So the answer for this question is both 2 and 3 are correct statements. Intake should enable water withdrawal during floods as well as dry periods, and it should be at a considerable distance from the treatment plant. It should be near to the treatment plant, and it should not be located at a downstream of disposal point of wastewater. So point number 1 is wrong. Point number 2 and 3 are correct. So that was the 7th question. Moving on to the 8th question. In transient state analysis for a given discharge, the drawdown due to pumping well in a confined aquifer is considered as a function of. Again, this, if you haven't gone to the lectures, this you don't have to know a lot of it. You can just understand. If you know what the word transient is, you'll be able to answer. Okay. Only Kiran has given an answer, which unfortunately is wrong. You were correct. Transient means it is unsteady. But here, when we talk about flow to wells in confined aquifers, when you have to consider the drawdown is a function of location. No matter whether it is a steady state flow or unsteady state flow, drawdown is a function of location. Now, when we say it's a steady state flow, drawdown will only be a function of location. That is, it will not change with respect to time. It will only change with respect to this R value. Now, if it is a transient flow system that we are using for the computation of drawdown, then it will vary with time. The drawdown is going to vary with time. So transient flow means both. Transient flow in the case of drawdown is a function of both location as well as time.
Yes, ma'am. I'll read it.
No. I mean, I understand transient term. First thing that comes into our head will be unsteady state. But when you consider drawdown is a function which is dependent on the spatial variable also. So when you talk about transient state flow in aquifers, particularly with the drawdown, it is both a function of time as well as location. Which of the following types of pumps require priming? Can anyone say what priming is? Just type in the chat box so you can unmute and say. Okay, never mind. Now, okay, take a guess. I mean, just think what priming might be, and if not, what are the pumps that require priming and what are the pumps that don't require priming? Okay, I don't see a lot of answers coming. So, priming means it is to submerge the pumps in underwater before it will start moving water. So in these given types of pumps, there are rotary pumps, jet pumps, centrifugal pumps, and reciprocating pumps. Centrifugal pumps and jet pumps requires priming, whereas rotary pumps and reciprocating pumps does not require priming. So if you refer slides 89 to 92, they have good details about what is rotary pump, what is centrifugal pump, what is reciprocating pump. So it will be useful for you to go through all the slides. And in the case of priming, only centrifugal pumps and jet pumps require priming. Rotary and reciprocating pumps does not require priming. Okay, moving on. This is a simple question. An aquifer bounded on both above and below by impervious strata, where groundwater is restrained under pressure, is known as. I gave the answer. Yeah, correct. So the answer is confined aquifer. So these are the various kinds of aquifer. Wait a second. Yeah. So these are the various kinds of aquifers. It's confined, unconfined, perched aquifer, and leaky aquifer. So unconfined aquifer is when there is no impervious strata and the water table is at free surface. Confined aquifer is when there is an impervious strata up and below. So because of that, the water is held under a particular pressure. Perched aquifer is an aquifer where in this upper strata of the soil, there will be an impervious strata. When it rains, only when but during rainy spells, water will accumulate on top of these impermeable impermeable structures, and then after a point of time, it will get drained out also. So these temporary kind of aquifers are called perched aquifers. Then there's leaky aquifers through which vertical movement of water will occur. Although it is a confined aquifer, this layer will have provisions for water to percolate in the vertical direction. That time we call it as a leaky aquifer. So these are the different kinds of aquifer: unconfined, confined, perched, and leaky aquifer. So the answer for the question will be confined aquifer. Aquifer bounded on both above and below by impervious strata. Now the 11th question. The most common conveyance system for water in water supply project is? Yes. Yep. A couple of you have given the answer as A. And yes, the answer would be A. It is pressure pipes. Okay. So there are different types of conveyance system. One is the channel and flumes. The other is tunnels and aqueducts, and the third type is pipes. So general type of common type of conveyance system for water is pressure pipes. pressure pipe looks like these. There are various types of materials in which they are made. Most of the time, it's the pressure pipes that are provided as a conveyance system for water. So yeah, that will be the answer. Now next question, question number 12. The specific retention of a soil strata with a porosity of 0.34 and specific yield 0.19 will be. So this is a small, very simple numerical. You can take your time, do the calculation. It's a very simple calculation. I'll give you like a minute. Yes, Mekanta Devan has given the answer D. Are there any more answers? Okay, one more person has given the answer D. Okay, now let's move on to the solution. So specific yield is nothing but the amount of water per unit volume that is drained from an aquifer because of the influence of gravity. Now specific retention is water that is remaining back after all the water from the aquifer because of the influence of gravity flows out. Whatever water that is remaining back, that is retained by the soil grains, is called the specific retention. Per unit volume is called specific retention. So sum of specific yield and specific retention is giving us a value called porosity. Porosity by definition means the volume of the voids in a soil. Now, soil is a complex matrix which is consisting of soil particles. There will be pore spaces. These pore spaces are called voids. So what is the volume of the voids to the total volume of the soil sample is called porosity. Now, when all of the water is filled, all of the pores are filled with water, it is going to be a saturated soil media. So that is giving us the porosity of the soil. So this is the formula for getting the porosity in terms of specific yield and specific retention. The sum of the specific yield and the specific retention is going to give us the porosity value, which is N. Here SY, the specific yield is the volume of the water that is drained to the total volume of water, and specific retention is the volume of the water that is retained in the soil to the in the aquifer. Soil material, when I mean talk about soil, I mean the aquifer material. Volume, that is volume of water that is retained in the aquifer material to the total volume that is remaining in the aquifer. So when you add those two, you'll get the porosity. So here we have been given the specific retention and porosity value, right? So the answer will be 0.34 minus 0.9. SY plus 0.19 is equal to 0.34. So 0.34 minus 0.19 will give you 0.15, and that is the answer for this question. Okay, now we move on to some little bit of numericals that are done in this chapter. You can take a look at the numerical. I'll give you like enough time. If you want me to give you enough time for this question, you can tell, or should I like move on to the answer? What do you suggest that I do? Okay, I'll do one thing. I'll wait for 1 or 2 minutes so that you can just go through the question. And if there are people who know how to do it, please do it. Give me the answer. 2 to 3 minutes. Yeah, sure. Please take your time, read the question. And then after like 2 to 3 minutes, we'll discuss the answer. Has anyone got any answers? Someone's there in the name of District Lab Buxer. Is there a name I can call you? Okay, shall I move to the solution? The first answer.
Is it 2 into root 0.55 meter, the diameter?
Okay, do you have the answer 2 into root of 0.55? I don't think so. That will be the answer. Okay, I'll discuss the solution. No issues. Okay, so here what we have been given, the values that we have been given is the flow rate. Q value is equal to 3.5 meter cube per second. Second, the first question here is asking us to find what is the diameter of the pipe that can discharge this much rate of water, 3.5 meter cube per second, and they have given the velocity of water flowing through this pipe is 2 meter per second. This one, we can make use of the simple formula Q is equal to AV. Discharge is equal to area into velocity. And here we have been given the discharge value. We have been given the velocity value. So area will be equal to Q by velocity. So the answer for the first question would be 1.5. Could you please excuse me for 1 minute? Okay, sorry, I had to take an important call. So yeah, the first question, this is the formula that would be using. Here is the formula A is equal to Q by V. Here Q is given as 3.5 meter cube per second. Velocity is 2. So that is equal to 1.75 meter square. Now in order to get the diameter of the pipe, we use the formula area is equal to pi d square by 4. So for the purpose of getting D, we'll use it 2 root of A by pi. That is the area by pi. We have got the area here. It is 1.75. So 1.75. Yeah, your answer will be correct. It will be 1.75 by pi the whole root into 2. That will get to around 1.493, which is almost equal to 1.5. Now moving on to the second part of the question. If the distance from the source to the reservoir is 1.6 kilometers, that is L. L is equal to 1.6 kilometer. The frictional head loss will be equal to what? Here they have given the friction factor is equal to 0.032 and they've asked us to find out the head loss due to friction. So for that, we will use the formula HL is equal to FLV square by 2GD. And here we have been provided with the statistics. F is equal to 0.032. L has been given here as 1.6 kilometers. So we have to convert that to meters. So it will be 1600 meters. Velocity has been earlier given as 2 meter per second. So 2 square divided by 2 into G value is 9.81 and D value is what we have found here, 1.5. So putting it directly in this formula, we will get the head loss due to friction is going to be almost 7 meters. So now the third part of the question is, find the horsepower of the pump that is required to assume horsepower of the pump required by assuming the pump efficiency 75%. If the difference in the water level of the sump and reservoir is 20 meter. So when this is said, the statement means that the total head, that is the suction head plus the delivery head, is going to be 20 meters. And also they have mentioned to ignore minor losses and take the specific weight of water is equal to 9.81 kilonewton per meter cube. So again, this here we are making use of the formula gamma QH by 746 divided by efficiency. So this is the formula for finding out the horsepower of a pump. Here gamma is 9.81 into 10 to the power, they've given 9.8 into 10 to kilonewton per meter cube. So that we are converting to Newton, it will be 9807 Newton per meter cube. Q is again given over here, 3.5 meter cube per second into H is equal to 27 meter. Now, how did you get 27 meter? Here they gave us the value 20 meter is the water level of the sump and the reservoir, difference in water level of the sump and the reservoir. That height, this is 60. I have just put this figure for reference. What they mean is the height between the surface of the sump and the surface of the reservoir is going to be the total suction and delivery head required. So that has been given as 20 meter. 7 will be the head loss due to friction, and they have asked us to ignore the minor head losses, so that value we are not considering. So total head is going to be 27 meters. So if you put it in this formula, divided by 746 divided by the efficiency. Efficiency they have given it as 75%. So that also you have to put in as percentage value only. So you will convert it to decimal as 0.75 and you will get the answer 1656.9 or 1657 horsepower. So basically this is what these are the types of numericals that will come in that entire portion. If required, I'll try to discuss a few more numericals in the next class with respect to this week 3 portion. This is another numerical that has been discussed in the during the sessions. Here they are also computing the population requirement, daily water demand. These are the formulas that are used that in the same problem that we have discussed now. Here they have considered velocity of 2 meter per second for a discharge of 3.89, and they got the area. From the area they got the diameter by again pi d square by 4 by finding out for D. After that the frictional loss is FLV square by 2 GD. Here F is 0.04. They have given it the friction factor as 0.04. Then L is what? 2.5 kilometers away from the river. So 2.5 kilometers converted into meter will be 2500 meters. Velocity they've given us 2 meter per second. So that will be 2 meter per second. They have calculated that value over here by 2 into 9.81 into 1.6 will be the diameter that we have obtained here. Here also they have said, see, section head plus delivery head is the head difference between the sump and the reservoir. So that plus the frictional loss means the head loss due to friction plus minor losses is equal to the total head required to pump the water, and BHE will be again gamma QH by 746 divided by efficiency. So this much is about the question discussions for week 3 portion. Does anyone have any doubt regarding these portions, especially the numericals? Could you please excuse me for 1 minute? I'll I'll be here. I just have to make a call. Sorry for the interruption. I had to make an emergency call. Okay, we'll get back to our session now. Yes, so this was the week 3's discussion. Now we'll move on to the week 2 population forecasting and water demand discussions, question discussions. So the first question goes like this. Estimation of water demand of a city is needed for finding out the required capacity of water intake for water withdrawal, required capacity of water treatment plant, required capacity of flow rate in the water distribution network, all of the above. Yes. Dharanjan, Mekantha, and Mujahid, all of you have given the correct answer. It's all of the above. So need for estimating water demand is Sangamitra. That's the correct answer. Water services are should be designed in such a way that it will take care of the future requirements also, and also for helping us to decide what kind of infrastructure needs to be set up. If we know about how much is the amount of water that required to be supplied only, we'll be able to decide what should be the pumping rate, what should be the pumping rate, what should be the reservoir capacity and all. It should be taken care that water should not be underestimated, neither be overestimated. So the correct kind of estimation of water demand is required. So it is all of the above. It should be for the required capacity of the water intake, required capacity of the water treatment plant, required capacity of flow rate in the distribution network. All of them requires the estimation of water demand. Now the next question. As per Bureau of Indian Standards, under domestic uses, the highest consumption of water is for drinking. All these are domestic requirements of water. Which out of these domestic requirements is consuming the maximum amount of water as per the codal provisions? Mujahid has said C, Sangamitra has said D, Mekant Tevan has said D, Dhananjayan has gone with B, Kiran is also going with B. Okay. So, according to the Bureau of Indian Standards, IS 1172 1983 Code of Basic Requirements for Water Supply, Drainage and Sanitation, the maximum amount of water consumption required is for bathing. After that, laundry. This is the discretization of the water requirement for domestic purposes, and the total requirement is 135 liters per capita per day. This value, this total value is a very commonly asked question. What is the per capita water consumption for liters per capita per day for domestic consumption is one question that is generally asked. So the total water requirement is 135, maximum is consumed by bathing. Now if we look at flushing and non-flushing system, and two systems are there. Full flushing system is when flushing is being applied to the toilets as well as urinals. When it is having a full flushing system, then the water requirement is 200 liter per head per day. If it is a non-flushing system, it is 135 liter per capita per day, and in both the conditions bathing is what is required, consuming the maximum amount of water. Here it is 75, here it is 55. So this is according to the Bureau of Indian Standards. Next question. Firefighting demand for a city or town is usually estimated based on what? Okay, so Dhananjayan said A, Kiran A, Mekkandathan A, Sangamitra A, Mustafa is A. All of you have said A, which is also the correct answer. So rate of environment is actually treated as a function of population. So different formulas are there, and all of them depend on the population of the city as the prime variable for its estimation. Now, question 4. For a city having a population as 1 lakh, which of the following methods or guidelines will give the highest estimate of water demand? Is it the Indian Standard IS 9668990, Pichling formula, Freeman's formula, or Buston's formula? Okay, so two answers, both are D. So these are the empirical formulas that are used for firefighting water demands: Baston's formula, Quichling's formula, Freeman's formula. All of this, one thing earlier, Dhananjayan had asked a doubt regarding not obtaining the answer. All of these questions are making use of the population in terms of thousands. So whenever you substitute the population, if you have 1 lakh population, you have to divide it by 1000 and then substitute that value in the P value. So these are the formulas for the fire demand, and this based on the population. If the population is less than 2 lakhs, this is the formula that is used. And if population is greater than 2 lakh, we use, this is the discharge value for 2 lakhs people, plus an extra 9,100 to 36,400 liters is used for the discharge. So if you go through the slide, you will have the common formulas and the what is the necessary discharge required for these formulas. So the answer here is Baston's formula. So here the given population is 1 lakh. So population in thousands will be divided by 1 lakh. If you divide by 1000, you get 100. So as per the Indian standard, fire demand is 1800 liters per minute for every 50,000 population. So up to 3 lakhs. So for 1 lakh population, the fire demand will be 3600 liters per minute. If you use all the formulas and calculate, you will get these are the values. So Baston's formula is giving us the maximum highest value. So that is why we are saying that it is the formula that is giving the highest estimate of the fire demand. You got this point right. As per Indian standard, for every 50,000 population up to 3 lakh, 1800 liter per minute is calculated. So that is why they are multiplying it by 2. Yeah. Dhananjayan has got one question. Please ask.
Good evening, ma'am.
Yeah, sure.
Regarding the formula, Freeman's formula,
Yeah.
in this slide,
Mhm.
it has mentioned 1136.5.
Okay.
P divided 5 by 10. This is the formula you have given it. But I have seen some reference. It has by 1136 P divided 10 plus 10. Both are same, or whether is it correct, ma'am?
Here they've written at times this is also used.
Oh.
Okay, so in case you're generally, I mean, for numericals, when I have studied and all, we use P by 5 plus 10. Some references might be giving this also. So I don't think so that value is going to change the answer altogether. So in case you want the exact answer, just do it with both of it. And then whatever option you have is giving the answer. If it is relating to either two of these formulas, you can choose that answer.
Okay, thank you.
Okay. So this is one important portion in water demand, the firefighting, these three formulas: Baston's formula, Quichling's formula, Freeman's formula, and the Indian standard method. I think doing this, I mean, knowing these three formulas itself will give you marks. It might be a definite question for the exam. So like I said, also remember, whenever you put the population value, take care that you always divide the population that is given to you by 1000 and then use that value. Also, the answers will always be in liter per minute. So in case they are giving liter per hour, you have to take care of liter per hour or liter per second. Always make sure to convert it to liter, obtain the answer in liter per minute. Okay, as per CPHEO guidelines, recommended per capita demand for water supply is lowest for. Is it for metropolitan cities, towns, or cities provided with pipe water supply? Or is it the same for all? Lowest for towns, Mujahid has said B. Devan also has B. Mustafa has also gone with B. Okay, so most of them have gone with B. We'll go into the answer. So, according to CPHEO guidelines, these are the recommended maximum water supply for domestic and non-domestic needs. So, towns provided with pipes water supply but without a sewerage system, recommended level is 70. Cities provided, it is 135. That is the domestic requirement that we had calculated. You can remember it like that. Cities provided with piped water supply where sewerage system is existing is 135. Metropolitan cities, it is 150. So the lowest here is town only. So the answer that you provided is correct. Moving on to the next question. Okay, the approximate peak hourly water demand of a city having annual average hourly demand as 1850 meter cube per hour would be approximately. You have to consider the daily peak factor is 1.8 and hourly peak factor is 1.5. What will be the answer? Peak hourly water demand is what has been asked. Annual average hourly demand has been given. Take the peak factor, daily peak factor is 1.8, hourly peak factor is 1.5. What will be the answer? I'll give 1 minute for everyone to just go through the question and do the calculations. Okay, so let's move on to the answer. So this is how the demands are calculated. So let's move on from the starting. Average daily per capita demand is the quantity required in 12 months divided by 365 into population. Now what first value we'll be using is maximum daily demand. What is the maximum daily demand is equal to 1.8 times the average daily demand. Now, in order to calculate the maximum hourly demand of the maximum day, that is called the peak demand. So you have to remember peak demand is the maximum hourly demand of the maximum daily demand. That is called the peak demand. So in order to compute that, what will we do? We will multiply 1.5 into average hourly demand on a maximum day. Again, you have to take care of this word maximum day. So average hourly demand of a maximum day is equal to what? The maximum daily demand by 24. That is, we are dividing the daily 24 hours demand by 24 will give us the average hourly demand for that maximum day. Now, what is the maximum daily demand? 1.8 into average daily demand. So substituting this value in this maximum daily demand, we will get 1.5 into 1.8 into average daily demand divided by 24 is giving us 2.7 into average daily demand by 24, which is equal to 2.7 into annual average hourly demand. So all these words are confusing, I understand. Let's go through it once again. First, here we are calculating the maximum daily demand, that is equal to 1.8 times the average daily demand. That part is covered. If they ever ask you what is the maximum daily demand, you will multiply 1.8 with the average daily demand and you will get the maximum daily demand. Now, in case they are asking you the annual average hourly demand, that is what they have asked here also. Sorry, they have asked you the peak demand and given you the annual average hourly demand. What we have to do is we have to substitute annual average hourly demand multiplied by 1.5 into 1.8. You will get the peak demand. So how are we getting the peak demand? We are multiplying 1.5 with the average hourly demand on a maximum day, which is equal to the maximum daily demand by 24 into 1.5. Maximum daily demand, since it is equal to 1.5, 1.8 into the average daily demand, we substitute that value over here and we get 2.7 into annual average hourly demand will be the peak demand. So this is the general peak factors that are considered while doing this calculation. Sometimes they will ask you to assign certain values. Instead of 1.5, they will ask you to do 1.6 or 1.7. So you have to take care of what values that they are provided. In case no values are provided, you can by default use 1.5 and 1.8. 1.5 for the average hourly demand and 1.8 for the maximum daily demand. So the answer here is 5,000 meter cube per hour. Here how they have asked for the peak hourly demand by giving us the annual average hourly demand. So that, like I said, 1.5 into 1.8, that is 2.7 into the annual average hourly demand will give us the peak demand. The peak demand over here is meaning maximum hourly demand of the maximum day. So this is an important slide that you have to learn. Again, like the fire demand, this is also one question that is sure to be asked. They will either ask the maximum daily demand or they'll ask the peak demand, or they can ask you what is the annual average hourly demand by giving the peak demand. Okay, next question. These are the design periods for some storage system and pumping systems. What are the design? I mean, match the following and get me the answer. I think only one give the answer. Okay. Mujahid, Kiran, Sangamitra all have given B as the answer, which is A3. Electric motor pumps 15, storage dams 50, distribution system 30. We'll go to the answer. So as per the design period requirements, storage by dams require the maximum design period, which is 50. Pump houses require 30. Electric motors and pump require 50. That was the question, I believe. Yeah. Storage dams, electric motors, pump, and distribution system. So storage dams are requiring 50, distribution system requires 30, and electric motors and pump require 50. So the answer will be B, A3, B2, C1. Okay. Again, this is according to CPHEO guidelines. Now, the 8th question, which of the following is certain to cause an increase in the population of a city? Migration, annexation, both A and B. Mujahid has said A, Kiran has said C. Okay, so the answer here is, the question asked was, will definitely cause an increase. So factors that affect the population change: birth rate will cause an increase, death rate will cause a decrease, migration can cause an increase or decrease, and annexation can cause increase. So birth rate and annexation are two conditions which will definitely cause an increase. Death rate is will decrease the population. Migration can either increase or decrease the population, because um, it's not a consistent thing. So the answer will be B. Annexation means when some territory is being taken under control. So that is going to actually add on the population of that entire place with the population of the person or the country which has taken control of the other domain. So the answer here is B, annexation. So 9th question, for cities of moderate size and age, the better suited method for population forecasting is. So here they've given 4 methods of population forecasting: arithmetic increase method, incremental increase method, exponential increase method, geometric increase method. Which out of this is the which is the best suited for moderate size and age? B, C, C. Okay, let's move to the answer. It's incremental increase method. It is the best suited for cities of moderate size and age. If you see this method, incremental increase method, they have written, I mean, in the slides for all the methods: arithmetical increase method, geometric, incremental, logistic curve method, all the methods, they have written what is the applications, the requirement, as well as the limitations. For cities of moderate size and age, it is incremental increase method. Now, arithmetic increase method is regarded suitable for population forecasting of. Now we have learned about moderate sized places. What is the what kind of place is suitable for an arithmetic to use an arithmetic increase method? Is it small to average cities or comparatively new city, large and established cities? Mujahidin said C, Kiran is saying B. Okay, let's go. Arithmetic increase method is regarded best suitable for large and established cities. And it is underestimating the population in small, average, and new cities. So here you can see about the arithmetical increase method. It is applicable for large and established cities, and it will give lower population estimate than the actual value if it is used for small, average, or comparatively new cities. So again, we learned about 2 methods: incremental increase method, which is giving us which is best suited for moderately sized cities. For large and established cities, arithmetical increase method is the best suited method. Now, which of the population forecasting utilizes the city's population saturation limit? Okay, Kiran has said B. We'll move. It is logistic growth method. Logistic growth method is considering the population. Population can't increase beyond the saturation population. So it is this method which is making of the saturation limit. This method is following an S-shaped curve, like all the logistic growth curve methods. Now let's move on to one of the numericals. The analysis of historical population data for a city showed population increasing at a geometrical growth rate of 0.25 per decade. The population of the city in 2021 census is 5,80,000. The expected population in 2041. So they're asking for 20 years. Per decade, there's a growth rate of 0.25. So making use of the formula for geometric increase method, population growth technique, we can find out the answer for this. I'll wait for 1 minute. You can just solve it and give me the answer. Kiran Behra has said the answer is A. Sangamitra also A. Okay. So geometrical increase method. This is a formula. The population is equal to the initial population 1 plus k to the power t. So when you do the change, here they have given 2021 to 2041 is increasing. Sorry, let me go back to the question. 5,80,000 is the expected find the expected population. 2021 it is 5,80,000 and growth rate is 0.25. So here, since the time period is 20 years, 2 decades. So n will be equal to 2. Growth rate is 0.25. So by geometric increase method into 1 plus this value to the power 2. 5,80,000 into 1 plus 0.25 to the power 2 as per this formula. This is the formula. PO into 1 plus k to the power t. T here is equal to 2. K is 0.25. P naught is 5,80,000. So at 2021, it will be 9,07,000. Nice work, Angamitra. Now this is a set of numericals. Please go through the questions. I'll give you 3 minutes or some good amount of time. Just solve it after reading the question. 2,64,000. Kiran and Mujahid. Okay. 14th one, that is using the arithmetical increase method. Now using the incremental increase method. Hi, did anyone get the answer for the 14th question? Shall I move on to the discussion of the solution, or do you need more time? Okay, move on. So I'll be moving on to the solution. So the first answer, like Mujahid and Ola said, it's 2,64,000. Second one, this is the answer. Third one, this is the answer. I'll show you the calculation. In arithmetic increase method, n is equal to 2051, 2011 is equal to 40 years, right? Yeah, 40 years divided by 10, n will be equal to 4. This is the formula, PO plus K into N, which is 136. Initial population given is what? Yeah. 2011 it is given as 1,36,000. 34 into 4. 34 is what value? Wait a second. Hold on. Okay, so yeah, this is the solution. I have a little doubt with the formulas. I'll just look into this problem and still explain if there's a little error in the answer. As of now, this is the answer. If there's any error, I'll let you know in the next class. Incremental increase method, this is the formula. And this is the values that are input. Average daily demand, like we had learned the earlier per capita consumption into population. We have found out the population, and then multiplying it with the per capita consumption will give us a liter per day. It is converted into million liters per day. So this was about the today's and this week's and last week's question answer discussion. Next week we'll discuss the questions relating to the week 4 lectures, and also a few problems from this incremental method and the week 3 session, because I see that a lot of you haven't gone through the lectures. So we'll do a few problems relating to these the third week's lectures also. For now, this will be it. If you have any doubt, you can ask, or you have.
This calculation is okay, I think.
This is okay. I just have a little bit doubt with the n number. If it is correct, it will.
No, n is 51 minus 11. So there are 40 years, means 4 decades. 40 years means 4 decades.
Okay.
So it is okay.
Okay. Thank you.
And in last week assignment also, such type of problems were there, and options were not there, only boxes were there. We have written only answers. Is it okay, or we need to do the calculations there?
No. You just need to put in the answer.
Okay. Thank you.
So that will be for today. Meet you in the next session. If you have any doubts, you can stay back or you can leave the session. And also you can make use of the discussion forum. If you have any doubts, you can post your questions over there and there'll be people to answer it. The PDF of PPT. Which PPT are you asking? The lecture material is available already in the course, with the course material. Today's, I'll see if I am not sure if I can share it with you. I'll just ask my instructor or the concerned authorities and let you know if it is something that I can share with you. In that case, I'll be commonly sharing it with in the course. Okay, you were late today. So which one do you want? From what portions do you want? I had actually, I'll show you the PPT. So since what question 1 to 6 in the week 2 or week 3 session? Week 3, okay. Week 3, this was the first question. The criteria for selecting water source include long-term availability of good quality of water, distance of source from the center of water consumption, or cost of water abstraction from the source and transmission to the treatment facility. The answer was based on this criteria. There are 4 major criteria, which includes first the characteristics of the. Okay, thank you, Kiran. Bye-bye. Regional geographical properties, feasibility for state-wise development and economics and cost. So all the options will be the correct answer for this one. Long-term availability, good quality water, distance from the source, cost of water abstraction, all these are responsible. In the question 2, what is the common type of shape provided for water entry in intake structures? The answer for this is bell mouth entry. Bell mouth entry in river intake structures, you can see here, this will be the kind of inlet that is provided. Third question, what is the type of raw water sources with appropriate example? These are the sources given. What are the which are the sources? Match the following. So in this, the answer is going to be groundwater source means we know it is aquifer. Atmospheric source means rainwater. Unconventional source means recycled wastewater. Surface water source is 1. So the option is A2, B3, C4, D1. These are the different sources of water for public water supply. Surface water sources, groundwater sources, atmospheric sources. This is one unconventional source. This is also pretty unconventional source. So this will be the answer. Fourth one, river intakes, if it is situated in a navigation channel, how is it protected? By providing a wire mesh or intake inlets, constructing a sufficiently deep intake foundation, or constructing a cluster of piles all around the intake, how is it done? So the answer for this is constructing a cluster of piles all around the intake. So that piles are constructed so that we can actually protect it from the force of the water that will occur if when ships or boats or whatever is moving through the navigation channel. So that is the kind of this provided. This you can find in the site design construction. Intake should never be constructed, should generally be not construction in a navigation channel, but in case it is done so, you can you have to protect it by constructing a cluster of piles all around it. The fifth question was, what is the B and the Q coefficient indicate in the drawdown formula BQ plus EQ square? So BQ plus EQ square is BQ plus EQ square is equal to SW is the formula for drawdown, and the option A will be the answer. It is aquifer loss coefficient and C is well loss coefficient. This is the sixth question. Please go. So for a pumping well located 100 meters away, left to a river, net drawdown is estimated by superimposing drawdown due to a discharge well with drawdown due to dash having same pumping rate. So the answer is an image recharge well located 100 meters away on the right side to the river. This is by the, I'll show you. So when you go by principle of superposition, whenever you have a boundary condition, in order to get the proper cone of depression, drawdown height and the cone of depression, what we do is we assume an imaginary recharge well exactly at the distance of this discharge well from the boundary and the opposite side of the boundary with an opposite condition. Here, if it is discharge, we assume here it has recharge with the same pumping rate. And from this, we can calculate what is the drawdown. So this value is going to be the actual drawdown over here if there was no river or boundary condition. Because there's a river over here, the constant head boundary is going to come. So the water level is going to go like this instead of going like going in the profile of the cone of depression. So these details are there in the slides. You can read a little more about the well flow with boundaries, without boundaries, with parallel boundaries and all. Will that be done, Mujahid? You said the question 1 to 6, right? Okay. You're welcome. Enjoy. Good night. Mustafa, do you have any doubt? I'm not sure if I can provide the slides. I'll just ask and let you know an update in the next class if I can provide or not. And this I'll just let you know after discussing with the instructor. If you don't have any notes, so we call it a day. You can leave the session if you don't have any notes. Mustafa? Good night.